ahead and get started. I am happy to introduce Megan Harkema. She's a fifth-year PhD student and she's studying nuclear environmental engineering at Vanderbilt. She received her degree in nuclear engineering from the University of Michigan. And her research interests include developing and applying novel safety analysis techniques as part of advanced reactor design and leveraging historical information and lessons learned from DOE test reactor operations. She has a particular interest in molten salt reactors as well. And I will hand it over to her so she can go ahead with her presentation.
All right, thank you, Lara. I appreciate that. So good afternoon, everyone. Give me just a second to get my slides up. Can everyone see just fine? Wonderful. Okay, so thank you again for that introduction. This afternoon, I'm going to be talking about some work that we as part of CRUST did, examining the decades-long surveillance and maintenance of the molten salt reactor experiment at Oak Ridge and some of the lessons that we can learn from that reactor as part of planning for advanced reactor design in the future. So first and foremost, just a little bit of a background on why CRUST performed this review of the MSRE and the Oak Ridge Reservation in general. So in February of 2020, CRUST was asked to conduct an independent evaluation of the human health and environmental risks and potential future impacts of facilities within DOE-EM's cleanup scope at the Oak Ridge Reservation. Now, primarily the scope included buildings and facilities previously used for defense purposes, but some of the facilities included were also previously used for nuclear energy R&D, such as the molten salt reactor experiment. And while performing this review, we at CRUST realized that this MSRE is one of the most interesting risk profiles that we evaluated during the project. So this reactor is actually one of 2 ever operated molten salt reactors across the globe, and it is presently being held in a surveillance and maintenance state by DOE. Now, this is sort of an interesting term used by DOE for facilities that have gone over or undergone some form of deactivation. So some form of material removal or stabilization, but further deactivation or decommissioning has been paused until appropriate funds or resources to do so have been identified. So the MSRE was a thermal spectrum reactor that operated with a graphite moderator, and it was also operated using both U-235 and U-233 as the primary fissile isotopes for the reactor. It operated from 1965 to 1969. However, even to this day, the fuel salt is still stored in the drain tanks below the reactor, which has presented a number of chemical and radiological hazards over the more than 50 years since the MSRE has ceased operations. Now, when performing our review at the Oak Ridge Reservation, we at CRUST were responsible for examining impacts to both facilities, as well as groundwater and ecological resources. So this human health methodology you see here is the methodology that we used in analyzing the facilities we were responsible for, including the MSRE. So to perform a review, we identified documentation pertaining to the MSRE, examined the hazards, potential initiating events, transport pathways, and potentially exposed receptors. And then we're able to rate risks to both sort of the co-located workers and the public based on this information. Now, what we are still in the process of doing is compiling all of our reviews here and putting them into a form that we can transmit to DOE to help them make decisions in the future in regard to the management of these facilities. Here is a sort of figure of the MSRE as it presently stands. You will notice that the reactor itself is below grade. This is fairly common for test and research reactors. It does complicate D&D occasionally, but MSRE is fairly far away from that, as I will talk about further in this presentation. So after the reactor ceased operation, the molten fuel salt was transferred from the reactor cell, which you see here, into these drain tanks at the bottom of the screen, into 2 of them particularly. Then the reactor itself was flushed with a clean non-radioactive salt that was also then transferred into this 3rd flush tank you see down here. Not pictured on this screen is the MSRE's off-gas system. Now, when it comes to an off-gas system, within nuclear fission, fission products are released, and these fission products have a Z from 1 potentially up until the Z of the isotope being fissioned. And so with this being said, some of these fission products might be soluble within the fuel salt, some might be solids that deposit on these structural materials, and some are actually insoluble gases that bubble out of the liquid salt itself. And so what we see is that we need a system called an off-gas system that can manage and collect these fission gases that evolve from the salt. The MSRE's off-gas system used a sort of charcoal bed cell to hold up those primarily isotopes of argon, xenon, and krypton that emerged from the salt until they could decay into non-radioactive isotopes that could then be sent out of the stack, which you see on the right-hand side of this figure here. Here is just a brief overview of where I'm going to go in talking about the impacts at the MSRE facility after its operation. Now, I'm not going to spend time going over every item on this timeline because that's the primary purpose of my presentation, but suffice it to say that there have been a number of different surveillance and maintenance evolutions for the MSRE since it ceased operations in December of 1969, and that these evolutions have been fairly challenging for DOE. And with that being said, the salt within the MSRE drain tanks is expected to remain there until approximately 2056. So this is almost 100 years after the reactor ceased operations. One of the primary concerns of the need for all of these different evolutions at the MSRE over the years has been the concept of radiolysis. So for those of us not familiar, molten salt reactors primarily use fluoride or chloride-based salts for operation. The MSRE used a fluoride-based salt, and fluoride salts in particular are susceptible to radiolysis. So the fluoride in that salt is a fairly light constituent, and when gamma radiation comes in contact with the fluoride salt, it can cause the production of free unstable fluorine or fluorine radicals that can interact further and cause the production of fluorine gas and HF gas if any water or moist air is present. Now, these pose a chemical hazard and also can increase corrosion rates of your structural materials. Further, if you have your uranium tetrafluoride constituent of the fuel present as well, that fluorine free radicals that are evolved can actually cause that to turn into uranium hexafluoride, which is a gas that can then migrate out of where you would expect it to be in your system. This actually became a major problem at the MSRE facility in the 90s. So for almost 20 years after reactor shutdown, so from 1969 up until approximately 1989 or 1990, the MSRE fuel salt was annealed. So it was heated to somewhere below the melting temperature, but hot enough that it would cause that fluorine to recombine in the system to prevent migration of any fluorine gas or UF6 or things of that nature from the drain tanks to other areas of the MSRE facility. However, in 1994, there were some high concentrations of fluorine gas and uranium hexafluoride that were found in the off-gas system. And further, there was a significant deposit of solid uranium that was found within the auxiliary charcoal bed that was in excess of 3 minimum critical masses. Given that this was a fairly significant criticality hazard that emerged, DOE and its contractors spent the next 5 years or so with input from the National Academies, the Defense Nuclear Facility Safety Board, TDEC, the Environmental Protection Agency, to develop and execute a plan to remove as much of the uranium that they could from the charcoal bed cell in what amounted to approximately 80% or 4 kilograms of uranium. To do so, they actually used portions of the facility's 50-year-old ventilation and off-gas system and developed additions and penetrations into that, which they now term the RGRS, which I will talk about further in this presentation as well. It's also important to note that this U-233 that has been removed from the off-gas system is actually still stored in a criticality safe storage container at the MSRE facility to date. So once DOE dealt with the sort of immediate concern, which was the potential for criticality in the off-gas system, they moved and transitioned into trying to prevent a similar occurrence from happening in the future by defueling the salt. So in 1998, a record of decision for the facility was drafted and indicates that the salt in the drain tanks needed to be melted and chemically treated to remove the uranium from the salt. Essentially, what we're saying here is that we need to melt the salt, expose it to HF and F2 through hydrofluorination and fluorination to actually preferentially create that uranium hexafluoride, and then pull that gas out of the system to remove the uranium from the salt. This was performed between 2004 and 2008. And was stopped when extrapolated measurements indicated that the concentration met the sort of treatment goal of 50 ppm in the tanks. However, later measurements actually indicated that the uranium concentrations were closer to 280 ppm, and although this is higher, it wasn't a level of concern that DOE determined would require further defueling, and so no further defueling has taken place. Now, this uranium inventory has been removed from the MSRE facility, but to the best of our knowledge remains at Oak Ridge National Laboratory, with the one caveat that there is an ongoing U-233 disposition project at ORNL presently, so the exact fate of this at the moment is slightly unknown. Now that we have removed the criticality hazard from the off-gas system and we have removed the uranium from the fuel salt, the MSRE has sort of entered a new era where chemical hazards become an interesting concern within the facility's safety analyses. So although the salt has been defueled, the fission products in the drain tank still result in the radiolysis-induced generation of the HF and F2 gas at rates of about 10 to the -3 kPa per hour within the headspace of the drain tanks. In order to prevent overpressurization when you have this constant buildup of HF and F2 gas, that reactive gas removal system I mentioned earlier is actually used about twice per year to pump the gases out of the headspace where they can be treated in aluminum and sodium traps. But when you're only pumping out gas from a system on a sort of approximately 6-month basis, you are still allowing a significant inventory of that HF and F2 to build up within your system. And under that present treatment scheme, the potential for HF and F2 exposure hazards to facility workers actually dominates the facility's risk profile more than any of the other radiological risks from the facility do. Because of this, DOE has transitioned to sort of developing a continuous purge system, which, as the name suggests, removes the HF and F2 generated within the tanks on a continuous basis. This is in the process of being implemented to the best of our knowledge. It may be starting very soon, if not already. But this project has experienced a number of delays in the procurement of essential vendor services, as well as impacts with COVID-19. Eventually, though, the goal is still to remove the salt from these drain tanks. And according to the original ROD, the 1998 document, the goal was to actually remove the salt from these drain tanks by February of 2003, which has obviously not happened for a number of reasons, which I'll discuss further. But an explanation of significant differences, or ESD, actually extended this estimate during the defueling process to 2007. And when attempts were actually started in 2008 to sort of remove the salt from the drain tanks, a plug developed in the transfer line and could not be cleared. This was because a thermal transfer mechanism, so essentially heating up the salt to the liquid form and pumping it out, was attempted, and this plug developed and they could not clear it. So since then, efforts to remove the salt have been postponed. In addition, some investigations have begun into other methods for salt removal. To that end, there was a 2019 engineering evaluation that was performed and suggested that actually mechanically suctioning the solid salt into segments and then loading it into transport or final disposal containers may be a more viable option. However, this would require a change to the record of decision for the facility. Furthermore, in addition, for motivating sort of the non-thermal transfer mechanism is the sort of concerns with structural integrity of the drain tanks and penetrations into the drain tanks. You have to remember that these are the original tanks that were developed in the probably 1950s, if not early 1960s, for use in the MSRE, and that they have held a highly corrosive substance for a number of years now, and in addition to that, have undergone a number of different thermal cycles. And so there are concerns with structural integrity of the tanks, in addition to all of the other concerns presented here. In terms of what would happen to the salt after it's removed from the drain tanks, that is still fairly up in the air. Los Alamos National Laboratory has done an analysis that can show that the fuel salt can meet the technical requirements of Defense True Waste, which could potentially make it eligible for disposal at the waste isolation pilot plant in Carlsbad. However, this would require a formal determination or approval to do so, and this has not yet been pursued, primarily because of the term defense in that Defense True Waste designation. The MSRE was primarily used as a facility for nuclear energy R&D. However, previous operations within that facility had been used for defense, so there is potentially some wiggle room to make an argument for it being defense-related waste. Just to sort of conclude with our observations here, I wanted to echo again that because of all these concerns, the salt is expected to remain within these drain tanks for a significant amount of time into the future. And it's reasonable to ask, so why do we care? This has been an ongoing problem for DOE-EM. It's a sort of one-off facility that may or may not be a big deal in the future. But we believe that there's additional lessons that can be learned here as well, primarily because molten salt reactors are one of 6 promising concepts identified by the Generation 4 International Forum as an alternative to the carbon-emitting technologies that are used for electric power production today. In particular, molten salts do offer a means to meet NRC expectations of enhanced safeguards and security resistance and ES&H risk reduction compared to commercial light water reactors. However, with that being said, and as I mentioned before, we only have 2 MSRs that have ever operated, which gives us a limited experience base to draw from during design when it comes to design and operations and surveillance and maintenance and the decommissioning experience. So it's important for us during the design process of molten salt reactors today to take the insights that we can from the MSRE to try to prevent similar occurrences within future reactors. And not only that, but we can take a sort of 30,000-foot perspective when looking at this case study for the MSRE and sort of translate that into other advanced reactor or small modular reactor designs being considered. Since one of the most important parts about advanced reactor design is responsible deployment and making sure that we have a plan for not only what we're going to do to design and operate these systems, but what we're going to do with the waste that's produced from them, including decommissioning waste. With that being said, our examination of the MSRE has sort of revealed that, like in many other areas of the nuclear industry, the system has undergone a number of delays or postponements of different procedures that were expected. And so with that, we've been working and trying to challenge advanced reactor designers to start planning and preparing for some of these delays at the present moment by asking questions like, are our reactor designs prepared to withstand significant delays in deactivation, decommissioning, or demolition processes due to regulatory, budgetary, or technical unknowns? Or how can the risk or hazard profiles of our reactor designs change during the retirement process? Are there phenomena that we can model and study now to help us prevent these issues from occurring in the future? Or do our present reactor designs include preventative and mitigative features to help reduce risk to workers and the public during these D3 processes? Or are the operational structure, systems, and components that exist within the reactors diverse and sufficient to reduce risk during D3? Since as we've seen with the MSRE, those risks can change over time. And lastly, are there potential delays in D3 due to supply chain or critical services procurement issues that could be anticipated now? For example, in the case of the MSRE, the use of some of these exotic materials that may need a lot of lead time to obtain. And so with that, I would like to thank you for your time today and ask if there's any questions. I'd be happy to answer them.
Since it's silent, I'll ask a question. So because the fluoride salts tend to be very corrosive, they've not had any issues with the off gas or other components in terms of corrosion?
So that's an interesting question, and they have recently, but it took quite a while. So with the RGRS system over the past probably 10 to 15 years, I would say a lot of their components and their valves are exhibiting failures. And when they're opening these things up, there's very colorful, thick deposits of stuff in there that
Fluoride
are
salts, yeah.
from corrosion and chloride salts. And so it took a while, but the aging and the sort of corrosion have definitely started to impact the structural.
Would they know if the tank actually had corrosion? The tanks actually had corrosion issues?
They are working on ways to examine that. It is very difficult to get in there and look
That's why
at
I'm
that
asking.
in detail.
Yeah.
Yeah, because of the radiation environment and because of the significant concrete structures that are in place to shield things. But it's one of the things that they need to characterize before they try to remove
If
it.
they had a leak, is there a place for it to go? Is there a sump or something that they would know?
If there was a leak, it would still remain within the significant concrete shielded area. However, there have been examinations of whether or not water could ingress into the sort of shielded concrete subgrade structure, and those have been deemed incredible. So
Okay, that's good, because as you are very well aware, it's very credible in other places at Oak Ridge. So that's good.
exactly. But the MSRE's analyses show that.
So the radiolysis does not produce hydrogen.
No.
Okay. It can't, or they haven't seen it, or is it too? So does it complex with the fluoride too quickly for it to be a hydrogen gas issue, a flammability issue?
From my understanding, yes, that's the
Okay.
concern. And if there is anything with hydrogen present, it's going to cause the production of HF and
Okay.
not a hydrogen gas issue.
That makes sense. And these reactors are graphite moderated?
The MSRE was. They don't have to be graphite moderated in the future. Some of the molten salt reactors being considered are actually fast reactors.
Good.
So no moderator needed.
Because we don't want graphite with a positive void coefficient.
No, we don't.
Thank you.
Of course, Kevin. I see Justin's hand up.
Hi, good afternoon. Justin Marvel, I'm with Department of Energy. I'm glad that we create such cool projects for you guys to look at decades later. And looking at the time frame, it seems like we're going to be supplying lots and lots of research projects going out hundreds of years on this sort of activity. A colleague and I were just sort of curious, being from the waste side, very curious about waste disposition. So that discussion on the LANL with a defense determination necessary for that true is obviously very interesting for me. And some of us with WIP being such a high commodity for disposal, but there seems to be some gray area there on this reactor with certain other controversial definitions that we have within DOE that may be like an HLW sort of definition. And I was wondering, high level waste, just curious if you had any thoughts or insights on that, or have thought about that.
I would be happy to provide my thoughts. I will sort of qualify them saying that they are my thoughts and not representative of DOE or anything of that nature. I do have concerns with immediately placing this into WIP. I mean, from the technical perspective, obviously it might be able to meet the sort of true criteria of the 100 nanocuries per gram or something like that, if I recall correctly. But even if you take the salt out, there are still going to be those radiolysis concerns. And so they have postulated using a sort of getter to collect any of the HF or F2 that generates, but there is obviously a limited life on those sort of systems as well. The amount of qualification that would be necessary before putting the salt into transport and disposal containers is a concern to me. So I mean, if you had to ask me, I think there's so many lessons that from the advanced reactor R&D side that we could learn from the MSRE salt alone, that if there was a way that, I mean, not really calling it reuse, but further study of the salt, which would give you time to sort of come up with a plan to dispose of it in the future. I think that would be more beneficial in the short to medium term than immediately trying to dispose of it in technical containers that we may or may not have developed sufficiently as of now.
Yep, thanks for that. I know this actually question came up 2 weeks ago at a presentation I was giving. And so I think it's very important when it switches from material to waste and the whole process, which gives us a lot of flexibility, but it is a very interesting question. So thanks for your insight on that.
Of
And
course.
nice presentation. Thank you.
Thank you.
And Justin, if it is HLW, you have to be very careful if you're going to try to make a borosilicate glass out of this stuff with fluoride. You'd have to really dilute it in a joule heated melter to make that work, or you'd have to go to a different kind of melter, which we really don't have on hand, even though we've tested in the past.
Yeah. And
So-
so, I mean, I think Betsy is on this call too. We were at a
She is.
conference a few weeks ago, and they were mentioning putting salt waste into Synrock. And the people who want to put salt waste into Synrock tend to be very positive about putting it into Synrock. But the biggest concern from our end is the loading, kind of similar to what Kevin was saying. It's such a small loading that you can achieve there that you have to be very careful.
When Synrock won't work for HLW.
Yes.
There's only one path for HLW, and that's borosilicate glass.
Mhm.
At the moment in the Federal Register. There's another type that you can make a ceramic titanate out of it, but that's no longer in the Federal Register.
Well, and Kevin, I think that's why it's exceedingly important that it's being managed as material right now with no waste determination being made yet. So all our options are still
Absolutely.
on the table, which is why we need to have smart people like you guys doing the research to help us figure out what we need to do in the future. So, yep, thank you.
But again, the final pathway, the final disposal option does help drive some of that. So that you are completely correct, but I was pointing out that where you decide to put it also can have an influence on how you would treat it.
And where we could put it now, what's available to us now.
Yeah.
Thanks. I'll be quiet. It's your presentation. Thank you again.
Of course. Okay, I'm not seeing any more questions, so I will stop sharing at this point.
Megan, thank you so much for your, does anybody else have any more questions for Megan? Okay, Megan, thank you so much for your presentation. It was really informative, and we're so grateful that you were able to share your research with us. So thank you very much.
Of course. All right, so I guess everyone have a wonderful weekend, and we will see you all in a couple weeks.
Thank you.
Thank you, everybody.
Thank you.
Take care.